Hello everyone and welcome to today's webinar. It is titled the Estimation of Spinal Loading During Lifting Using Inertial Motion Capture. My name is Christopher Iversen and I will be the host of today's webinar, and I will be here with my colleague Morten Lund, who is also an R&D engineer here at Anybody Technology.
Yeah, hi.
So today we have an external speaker who is Frederik Greve Larsen, who has a master degree in sports technology from the University of Aalborg. And Frederik is going to give his presentation in a minute or so. But just before we start, I will just give a general introduction to the Anybody modeling system, and to those of you who is not familiar with the software or not familiar with musculoskeletal modeling in general. But first of all, what is the Anybody modeling system? Well, the Anybody modeling system is a software that allows you to do musculoskeletal modeling. As input, it takes motion data as kinematics and forces, and then it output body loads, which could be joint moment or muscle forces or joint reaction forces. And here in the bottom at the screen, you can see a screenshot directly taken from the software. Right now, the Anybody modeling system has been used in various areas of in a wide variety of areas and applications. And a few examples of this is movement analysis. It's product optimization designs. It could be in the field of sports, orthopedics, or rehabilitation in general. And it can be used to optimize or design assistive devices. A general workflow in the Anybody modeling system could look something like this. You can provide some kind of motion data as input, and then you can use some body models which you have created yourself or others have built. Then you can provide some kind of environment model, which could be an exoskeleton, as is the case with this example. And you can use Anybody to combine all of these things and run the inverse dynamics simulations to calculate the internal body loads. And the internal body loads being muscle forces or joint moments. You can then output the results and use it for post-processing with, for example, some finite element tool. But many users also closes the loop completely by doing some kind of design optimization and run this cycle multiple times. And this actually brings me to the end of the introduction, and I'll give the word and present the role to Frederik instead, and he can do his presentation. Thank you.
Thank you. So thank you very much for the introduction, Christopher. So today's webinar is going to be about estimation of spinal loading during manual material handling using inertial motion capture, and it's going to be based on our recently published paper. So just to give you a little background on this webinar today. So of course it's about musculoskeletal modeling and how it's applicable for analysis of human movement. And the reason why it's really relevant to analyze the loadings of the low back is because the low back is one of the most frequently body parts where people sensate pain. And to really understand how pain occurs, it may be relevant to look into how the loadings are at the low back, because if the loadings are high, a biomechanical explanation can be that damage occurs to structures in the low back that can feel to the sensation of pain. So one way to assess the loading of the lumbar spine could be to use a 2D biomechanical model, as you can see here. So to use this kind of model, it's fairly simple actually. You just need to have a estimation of how much flexion you have in the trunk, which you can get by putting in some kind of angle, and then you need to have an estimation of the burden the person is lifting. However, these models have been tested quite a few times, and it's shown that they are not as accurate as, for example, a complicated 3D model. So another way to analyze the loading of the lumbar spine can be to use a complicated 3D biomechanical model. They are most typically used in a laboratory where people use optical motion capture systems to measure the position of the segments and also measure the external ground reaction forces with the force plate. this kind of equipment is fairly expensive, and it's also very difficult to take out of the lab and use in the field. So that's the reason of this study, more or less. So we want to investigate how well we can use inertial motion capture sensors. So it's a kind of sensor, as you can see on this person standing here, that you can easily attach to the body in the field. These kind of inertial motion capture sensors, they are consisting of 3 parts, so an accelerometer, a gyroscope, and magnetometer. And by using these kind of sensors, you can estimate the kinematics of the human body. And when you have the kinematics available, you can also predict the ground reaction forces that have been investigated before, both for optical motion capture systems, but also for inertial motion capture systems. But it haven't been investigated before how the joint reaction forces, for example, in the lumbar spine are agreeing with a complicated 3D biomechanical model. So that's basically the aim of this study today. The aim is to evaluate the concurrent validity of a musculoskeletal model driven exclusively using inertial motion capture data and ground reaction force prediction for estimating L4, L5 spinal forces during various lifting and transferring tasks. And here, the biomechanical model, you can see the placement of the L4, L5 joint. So in order to do this computational study, we of course also needed some experimental data. So we recruited 9 men and 4 women, and we asked them to do some standardized lifting tasks, as you can see here on the right side. They did a symmetrical lifting task, they did an asymmetrical lifting task, a transferring task with a box, and a transferring task with one hand. The symmetrical and asymmetrical lifting task here were performed with 5, 10, 15, and 20 kilograms for the symmetrical task, and 5 and 10 kilograms in the box for the asymmetrical task. Then we recorded full body kinematics using a Qualisys optical motion capture system. As you can see, all the small dots here shining. And then we also used the Xsense MVN, a window suit, the inertial motion capture suit, to track the full body motion. As you can see, these orange sensors here. And then finally, we measured the external ground reaction forces as a reference for the predicted ground reaction forces. So in the next slide, I'll show a flow chart illustrating the flow of the computer simulations. But before I go into this slide, I just want to say a few more words about the inertial motion capture simulations in the Anybody modeling system. So basically, the input to the modeling system is the signals for the IMU sensors. But before we get the signals, we of course need to apply the sensors to the human body, as you can see here of the animation. You need to measure body dimensions such as, for example, foot length, hip width, arm span, height, and so on. Then we need to do a calibration of the model, and then we can do our measurements. And after we did the measurements of the lifting tasks, so the symmetric, asymmetric, and so on, we used the reprocess HD function to get even smoother or better signals from the Xsense. After we reprocessed the data, we exported the BVH file, and based on this BVH file that is containing all the motion data, we constructed this virtual or this stick figure in the body modeling system. And that's just being done by using the model in the repository. And after this, the stick figure is combined with the musculoskeletal model, where there are both virtual markers on the stick figure and on the musculoskeletal model, and then by using an optimization routine in the modeling software, we get the best fit of the musculoskeletal model. So basically, it's very similar to using an optical motion capture model. We actually get some position data that is being solved for the Euler angles, and then we are having the kinematic solved. And when we have the kinematic solved in the Anybody modeling system, we can predict the ground reaction forces that have been shown several times before by using this method of having these contact elements underneath the foot that are being activated whenever the foot are close to the ground. And that's basically what you can see here in the next slide. So you can see here we have the inertial motion capture model with the predicted ground reaction forces. And you can see whenever the person is moving the body up and lifting the box, you can see there were some activation of these contact elements. So this is the model we are primarily interested in, how it agrees with the reference model down here. I will come to in a minute. And the next model we have is the optical motion capture model with predicted ground reaction forces. So this uses the measured position data of the reflective markers, and then it goes to the routine of the Anybody software, where we optimize the markers, we solve the kinematics and solve the inverse dynamics. And then the last model we have is the optical motion capture based model with measured ground reaction forces and moments. As you can see, we have the force plate here in the bottom. And it's very important here to highlight that this is the reference model, it's the silver standard, and we are primarily comparing the first model up here with this one down here. But this one is also very nice to have, because with these two models we have the same kinematic data. So we basically see if the differences is occurring because of the kinematics or if it's because of the prediction of the ground reaction forces. So moving on to the data analytics and statistics. Of course, there were a lot of parameters that could potentially be investigated in this study. So here in the presentation, I will primarily focus on the trunk flexion, the vertical ground reaction forces for the right and left foot. I will focus on the joint reaction forces between the L4 and L5 disc. And I will also give a little information on the erector spinae muscle forces. Of course, we also used a lot of different statistical tools, but just to keep this presentation a bit more simple, I will focus on just showing the figures and using our vision to look at the figures and just get an intuitive understanding of how well it agrees. And if you're really interested in getting the exact numbers of the interclass correlation, the root mean square error, the relative root mean square error, or the Bland-Ullmann limit of agreement, I would highly recommend you to go and look in the study and see all these numbers individually. I will of course highlight some of them, but I will not tell you about all the numbers. So the first result I will show here today is the result for the symmetrical lifting, more precisely the vertical ground reaction force. So here we can see we have both the right and the left foot, and this is really important because this is one of the only direct comparison that is feasible to see here in this study. We have the inertial motion capture model with the predicted ground reaction force in red, and we have the optical motion capture model with black here. And just visually inspecting the figures, we can see the blue, the two optical models, the blue here with the prediction of ground reaction forces and the optical model with measured ground reaction forces agrees best. And that's going to be the general finding of all the figures I'm going to show later on. So I'm not going to highlight this agreement again. I will focus more on the inertial motion capture model and the reference silver standard. And that's because the difference in the kinematics is the input to the scaling, and here we see it's affecting the prediction of ground reaction forces, and that's of course a finding as well. However, if we look into other studies in the literature, we can see that the statistical findings, so the agreement or the accuracy of the agreement is fairly comparable to, for example, Cand.Scient.Tech 2019 that investigated walking. So that's more a simple movement, and it's really interesting to see we have a similar accuracy, indicating the algorithm for prediction of ground reaction forces and moment are working fairly well also in this situation. Another really interesting finding is that the agreement for the right and the left foot for the inertial motion capture model and the reference model is fairly stable for both right and left foot and all the different increments of load. And that's basically indicating that the muscle recruitment algorithm is able to distribute the ground reaction forces accurately, despite there are several close kinematic chains in this analysis. So that's a really nice finding. So some of the other movements we analyzed was these asymmetrical and transferring tasks. And here again, if we just visually inspect the agreement between the inertial motion capture model with predicted ground reaction forces and the silver standard, we here again, like we did before with the symmetrical lifting task, find a similar good agreement. And that's again confirmed by all these statistical comparisons we did. So the interclass correlation, root mean square error, relative root mean square error. So this output here is the symmetrical axial, or this output is for the symmetrical lifting, and it's the axial compression force between the L4, L5 joint. And again, here we have the 5, 10, 15, and 20 kilograms of load for each of the different lifting tasks. And visually, we can again inspect the figures, and we can see there is still a fairly good agreement, both in terms of phase and also in magnitude for the inertial motion capture model and the standard reference. However, it may look a bit like there is an effect of the increase of load, but it's only visible when we use the root mean square error, when we normalize to the size of the magnitude of the load. Then it's actually a fairly stable error we get between the inertial motion capture model and the optical motion capture model, and this is indicating that there is very small, if any, effect of increasing the weight of the burden the persons are lifting in these simulations. And then if we look then at the asymmetrical and transferring lifting task, again for the axial compression force, we see again fairly good agreement for the asymmetrical lifting task confirmed by the statistical analysis, but when we look at the transferring task, we see slightly lower agreement between the inertial motion capture and optical motion capture models with measured ground reaction forces. Another way we can look at the agreement between the different biomechanical models is using the Bland-Altman limit of agreements. However, when we expected the time series signals, we used the whole time series for this Bland-Altman analysis, we found the data were not normally distributed. So therefore, we decided to take the median, the 5th, and the 95th percentile for comparing the inertial motion capture with the optical motion capture systems. And overall, I would like to highlight the overall findings. So when we combine both symmetric, asymmetric transferring in one category, we can see the inertial motion capture model underestimates the axial compression forces with minus 10 percentage of body weight, while the optical motion capture model with prediction ground reaction forces overestimates the axial compression forces with 6.45 percentage of body weight compared to the silver standard with measured ground reaction forces. Although there are some differences for the inertial motion capture model, as we see here, especially with the 5th and 95th percentile, we still see, for example, using the interclass correlation, there is a good to excellent correlation, indicating they agree to a good extent. And we therefore, based on these results, believe that this kind of analysis, so using the inertial motion capture model with predicted ground reaction forces, can be used to get reasonable estimates of the L4, L5 axial compression forces under these dynamic conditions in the field. And this, as mentioned in the background and the start of the presentation, is something that has been very difficult to obtain easily before. So having these kind of analysis tools available is really useful. And especially we believe that it can be very useful to use as an ergonomic tool to compare the relative loadings between, for example, two different lifts in a workplace, or to compare the effect of intervention when we use the same kind of instruments, so inertial motion capture models with predicted ground reaction forces. Another parameter, as I mentioned in the aim, is also the anterior-posterior shear forces. So when we lift a box or any burden, the lumbar spine is of course exposed to both axial compression, but also to shear forces in the anterior-posterior and medial-lateral direction. And when we look at these anterior-posterior shear forces, just by visually inspecting, it's looking a bit like there is a trend to lower agreement with increase of weight. So if we look at symmetrical lifting with 5 kilograms here, the difference or the error compared to the optical motion capture model with measured ground reaction forces is slightly lower, both if we use the root mean square error, but also if we use the normalized relative root mean square error. So basically we see a small tendency to bigger errors in the anterior-posterior direction for the shear forces when we increase the weight. And that is of course something we need to be aware of if we use this kind of simulation in the field to try to understand the loadings of the lumbar spine, and then trying to use this as a biomechanical description of why people may experience pain during a working task or in the long run. And here again, looking at the asymmetrical lifting, we can see, as I mentioned before, a trend to less agreement when we increase the weight from 5 to 10 kilograms. And we can also see, although they follow kind of the same trend here for the transferring task, that the transferring task is also not as accurate as, for example, the axial compression. And then the last orthogonal direction for the joint reaction forces in the 4L5 joint is the mediolateral shear forces. Overall, we can see the magnitude of these signals is fairly low. And when we use the statistical tools to compare the accuracy, we can also see that, for example, the correlations are low, or we can also see the relative root mean square errors are high for all the lifting tasks, both the symmetrical and also here for the asymmetrical and transferring task. But that's kind of expected, because as we know from other studies, also when people are trying to predict the ground reaction forces, it's more difficult to get the mediolateral and anterior-posterior ground reaction forces as accurate as, for example, the vertical. And this is related to the fact that the magnitude of the vertical ground reaction force is most typically higher than the sideways forces. And this is kind of the same problem we have here. And it may be that if these mediolateral shear forces is of a higher magnitude, then we would get a better agreement between the inertial motion capture model and the optical motion capture model with measured ground reaction forces. However, this is only speculative and would potentially need to be investigated if someone finds this is a very interesting parameter for their study. And then another very interesting and quite unique parameter to investigate using this kind of analysis is, of course, the muscle forces. Because when we do musculoskeletal modeling, we have also the possibility to estimate these muscle forces. And in this study, we decided to investigate the erector spinae muscle force for all the different lifts. And here we see kind of the same problem as we saw with the anterior posterior shear forces, because here again, when we just visually inspect the figures, and also when we look at the statistical numbers, we can see that the agreement between the inertial motion capture model and also the optical motion capture model with measured ground reaction forces, the errors tend to get higher with the increments of weight. And we can see this both for the symmetrical lifting task, and we can also see it here that the error seems to be higher and is higher when we use the statistical tools for the asymmetrical lifting for 5 to 10 kilograms. So that's also something we need to keep in mind. And if we want to give an explanation on why this may be happening, it kind of falls back to the kinematic input, as I also mentioned on the vertical ground reaction forces, because the kinematic input is different. So it may be that the segment length and then also the length of the muscles and so on are different with the inertial motion capture model, and then we get these errors between the inertial motion capture model and optical motion capture model. So it kind of falls back to the kinematic input, because when we look at the optical motion capture models with predicted ground reaction forces, with blue here we can see it follows better the trend as the optical motion capture model with measured ground reaction forces. So the last finding and the last parameter I want to highlight here in this presentation is the pelvis thorax orientation. So it's basically on the trunk flexion. And as you can see here, there seems to be quite a big difference between the red line, the inertial motion capture model, and the blue, which is also the black because it's the same kinematic input. And this may be one of the reasons why we see these differences in, for example, the anterior posterior shear forces. And it may be related to the fact that the spine is a very complex structure. It consists of both the cervical, thoracic, and lumbar part, and this totals a lot of joints when we look at it. And then we need to drive this kinematically. And kinematically in anybody, the spine is modeled using this spine rhythm that distributes the motion over the spinal joints. And because in the inertial motion capture model, the pelvis is only driven by this model that is placed on top of the sacrum. And then it may be that the inertial motion capture system is not getting enough information to give an accurate kinematic description of the lumbar spine. And we need to remember that the optical motion capture model is both driven with reflective markers anterior and posterior on the iliac spine, and therefore it might be that the optical motion capture model is more accurate. But again, we need to remember that also optical motion capture is only an estimate, and it's not a golden standard for measuring kinematics. So with all this amazing data being presented, I would like to conclude on it. So overall, the inertial motion capture model with predicted ground reaction forces have here been shown to be possible to estimate the musculoskeletal loading during manual material handling tasks under dynamic conditions. When we, for example, compare the accuracy of this analysis to other studies also using the same methodology, using anybody as software to solve the inverse dynamic problem and get the joint reaction forces, the accuracy in this study is slightly lower, and it is kind of expected because we introduced the burden, so the box or the one hand weight in this study, and it's adding more complexity to the equations of motion and to the mathematics that are being solved to get the results. So that's kind of expected, and now we have a measure of how much it matters that we add, for example, the box or the one hand transferring lift with a burden in the hand. So overall, the inertial motion capture models, they might be very useful and show high potential to be useful to track relative changes in the axial compression forces in the lumbar spine in the field. So with this being said, I would like to give the word back to Christopher.
Yes, thank you very much for this interesting presentation, Frederik. Before we go to the Q&A session, we would just like to say a few words, so I will just take the presenter role back. Yes, and now I'll just give the word to my colleague Morten Lund, who will tell us a bit about the new BVH improvement in the new version of the Anybody modeling system.
Thanks a lot, Christopher. So I'm an engineer here at Anybody Technology, and many of you who have watched this webcast might actually go out and try some of these models if you download the Anybody modeling system. And I just want to point out that if you do, you have to make sure that you have the newest version of Anybody, because a lot of things have improved with the BVH model, also since Frederik has worked with them. So ensure you have the newest version, and you can see the versions here. It's the newest version of the Anybody modeling system and the accompanying model repository, which has all these example models. And in the model repository, there is a model where you can get started with this BVH model. It's already set up, and it's using an example file from the Cand.Scient.Tech system. All these virtual markers, they are attached to this BVH rig in the new version, and these markers, they are automatically calculated now by the Anybody modeling system when the model loads. Previously, it was really part of the model, and it required a pre-process step, which had some difficulties. It could, for example, have angle jumps, and there were many solutions to some of these things, some of these kinematics. And therefore, so I really recommend that you use the newest version. Also, on a side note, you have to remember that with these inertial mocap systems, if you have bad accelerations, you will also get bad data. And this is especially true for very dynamic motions. And we've generally seen that the Cand.Scient.Tech system performs really, really well. But we have seen other mocap systems that can give, or inertial mocap systems that can give problems. But it's really easy to recognize. So if you have, for example, a model where it's doing gait, if you plot the accelerations of the center of mass, or just maybe the pelvis frame in your BVH model, if those accelerations look weird, you cannot expect to get real forces, because, like, force is mass time acceleration. So if you have bad accelerations, you will get bad forces. Some of you might have been using older or previous versions of this mocap model, and if you want to upgrade your model or update your model with this new improvements, there's also help to do that. If you find the documentation for the model repository, and you find the documentation for the inertial mocap example, you can click that, and there is a description of how to update older models to use the new facilities. So yeah, with that, I'll give the word back to Christopher.
Yeah, so just before we go to the Q&A session, I just want to let you know that if you want to know more about Anybody and the Anybody modeling system, you can go and check out anybodytech.com for events and special dates, and a full publication list of all the articles which have been using Anybody modeling software and had done some kind of publication. We would also like to highlight a website called anyscript.org, where you can go and find the link to the wiki page and the link to all the repository sites. Also, a very interesting thing is the forum, which is also located here at the anyscript.org. And if you need any kind of help for some fellow Anybody users, you can go there and ask their questions. And I would also like to point your attention to the next webcast we're having. We're having a webcast May 6th, which is titled Subject-Specific Lower Limb Modeling and Evaluation with a Force-Dependent Kinematics Natural Knee Model. And as something new we're doing here at Anybody, we're hosting this webcast both in English and the day after in Spanish. So if you have some colleagues or anyone who would like to see the webcast in Spanish, then please go and spread the word. And if you have any questions or want to meet up, then please feel free to send us an email at sales@anybodytech.com and we will get back to you right away. So I think this brings us to the Q&A session, and I'll read some of the questions from the audience. So Frederik, are you able to hear me again?
Yeah, I can hear you.
Yeah. So one of the questions we have been giving has been that how did you actually attach these boxes you were lifting to the IMU model?
Yeah, it's a pretty good quick question actually. So we did it quite differently for the optical motion capture model and the inertial motion capture model. So in the optical motion capture model, we basically just attached some reflective markers to the box. So whenever we have a rigid body or a segment we want to drive, we just need to put 3 reflective markers on it. So that's basically what we did with the reflective, with the optical motion capture model. And on the inertial motion capture model, we fixed the box to the hand using a joint in the Anybody modeling system. And after having kind of described the position and the rotation of the box, we just needed to put in some additional information. So we of course needed to put in the mass of the box or the burden they were lifting with one hand to get accurate estimation of the equations of motion, and we also needed to put in the center of mass and inertia of the box. However, we modeled the box and the burden for the one hand lift in SolidWorks, and we were actually able just to export all the needed data using the tool you have available. And then after we had both driven the box or the burden in the system, and we have had the box attached to the hand, we just needed to apply a node on the box so we could fix the burden to the hand and then make it possible for the model to generate forces between this node on the box and the hand. So basically the box and the burden for the transferring task were glued to the hand.
Okay. And another question from the audience is, so what is the impact of using markers given by Xsense on scaling and joint kinematics compared to the scaled kinematic chain and joint kinematics given by Xsense?
Can you repeat the question again?
Frederik, I think what they are asking is that it may sound like that you were using the markers on the X from the BBH file to actually optimize the size of the Anybody model, as you would usually do maybe with traditional mocap.
Okay.
So I also got that impression when you gave the presentation, but I know at least that in the built-in model example that we ship with the Anybody modeling system, the models are directly scaled from the Xsense rig, you could say. So if it has a certain size, the model gets a certain size. We don't use the markers directly to optimize the model, but of course
that was a poor explanation. So you are completely correct that when you use the Xsense system, you manually use a measuring tape or ruler to measure the length of the different segments, and then you put this into the Xsense software.
Yeah, but the other approach would have been possible for sure, and it may also be that would be an advantage. I don't know, but it's not something at least I have tried.
No.
But it is possible to do in the same way with mocap data. So I will leave that to some of the audience to try.
Yeah, and you could potentially just decide to take the angles from the Xsense motion capture system and export these and use these exact joint angles to drive the model as well. But
yeah, that generally works really bad, unfortunately, and that is why we export these markers, because when you export the markers, you can filter the data on a position level, whereas applying filters to to angles which are sort of, it's basically kinematic chains of angles. If you apply low pass filters to that kind of data, you usually end up with some really bad results. So that's the whole point about getting those marker data out of the BBH file and using those instead to drive the model. That has some big advantages. Also, if the kinematics of the mocap model, the kinematics of the musculoskeletal model does not match exactly the kinematics of the BBH rig, and they are two different models, then it's hard to transfer those angles directly. So that might that is why we use these virtual markers.
Yeah, totally agree.
Yeah. So another question we got was, how did you actually define the start and the end of the lift cycle on each condition?
So actually, I didn't talk about it, but we actually had a force plate underneath the burden for example, the lifting, symmetrical lifting task. And actually we used the threshold based on this to segment the lifting cycle.
Yeah. And another question we have here, we have one from the audience asking that if we have measured ground reaction force with inertial mocap, does that increase the accuracy?
I think there might be another problem that then would be arising, because these inertial motion capture models, and we also experienced it quite a lot ourselves, are prone to drift, so they might change a bit orientation in the room. So it might be different to synchronize or make sure that the orientation of the force plate and the inertial motion capture model are accurate to get good results. I haven't experimented with this myself, but I could imagine this would be a problem. I don't know if you have any additional comments on this.
Well, I agree. These inertial systems have a tendency to drift maybe a little bit, and you don't know how the two, like if you were to collect ground reaction forces, you would have basically two coordinate systems that you have to align. We have a colleague who's working on this problem, but they also have pressure sensors on the ground, and they use the pressure to know, okay, now we know that the foot is exactly here, and we can maybe use that information to say something about the absolute position of the BBH, so of the inertial mocap data compared to the ground reaction force. But in general, it's not easy to combine these two things.
Yeah. So another question for you, Frederik. Do you think this approach with the IMU and predicted ground reaction forces could be used with exoskeletons?
Sure, I guess it could be possible, yes. I think you guys have an even better background to answer this question than me, since you probably have been doing quite a few simulations on exoskeletons.
Yeah, well, we have been doing some, and I also know of some of our clients who've been doing these kind of things. The big advantage of using an IMU system for these things is that you can actually go out to the lab floor or to the factory floor and get real data for people, so you don't have to be in the lab. So that's a big advantage.
But then I would assume a very big challenge would be to get a good understanding of how the exoskeleton are then interacting with the body, because then you would need to either use a pressure mat or a strain gauge sensor to get some additional information of how much load is, for example, the exoskeleton applying to the shoulder, if you have exoskeleton that are spanning the shoulder joint.
Yeah, or maybe you are designing the exoskeleton, so you're using the inertial mocap system to actually get the kinematics, and then you optimize the exoskeleton to provide the best lift or support in certain ways. And this means that you decide what the load of the exoskeleton should be on the body. So there are many use cases here.
Yeah, it's a good idea.
Yeah, so I think that will be the final word of today. So thank you very much for the presentation, Frederik.
You're welcome.
And yeah, and for the rest of the questions from the audience, we will address it right away, and we'll send an email to you with an answer. And if any of you have any more questions, please feel free to send us an email on sales@anybodytech.com, and we'll try to answer all of your questions. Thank you very much for attending this webinar, and I hope you all will have a look at the Anybody modeling system if you think it's interesting. And yeah, please let us know if you have any questions.